how the multi-layer neural networks work. And in that process, we talked about how do you train neural network and what learning means, right? That's what roughly we talked about. So I'm going to continue with that. Our main focus today is the language model. How do you take the neural network and then see what the language model is or should be? Because one of the things, if you remember, I said that your design of neural network depends on what your use case is. So we're going to consider one use case today, which is a word model or language model. Okay? So a quick review of what we did, which is the artificial neural network. 2 questions which came to revise a few things that we talked about yesterday. That's fine. After we take the break, we can revise it a little bit. But very quickly, what we did yesterday was that we defined what a neural network is. We said there's one input layer, one output layer. There could be one or more hidden layers. Does anyone remember why we needed hidden layers? Sorry? Okay, something else. Both of those are true, but like, what's the more fundamental reason? So basically, to solve a complex problem using linear functions, if we can, because we saw that we can implement AND and OR gate using a neuron, but we cannot implement the exclusive OR gate, right? The other thing, what we talked about somewhere here, I wrote the latent space. The hidden layers basically contain what we want or what we say about the latent space. That's what, and we'll continue to see that as we go on today, right? Any single neuron, and we had a couple of slides on that where we model a single neuron standalone and in between any previous layers. In general, there are inputs to the neuron. It sums them up, pushes it to a function, and then generates an output. This is roughly what a single artificial neuron works, right? You have inputs, input values, you have weights, there's a bias that's added, you sum them up, you make them through an activation function, and you get an output, right? And we said that there's a sigmoid, and then there's a softmax layer or softmax neuron, which basically generates softmax layer, which has neurons which can generate a probabilistic distribution of whatever the output you're looking for, right? So far everybody's clear, right? So given a problem, let's say not very complex, theoretically speaking, you should be able to sketch out a neural network that you can potentially claim that it will solve the problem. Is that correct? Did anyone walk through by hand the AND gate and OR gate and arrived at those weights and biases? All right, so your theoretical model will not work then, because you have to make sure that you can walk it through and then see the weights and biases that I used yesterday in my slide are actually working or not. And start with some random numbers, go through a couple of iterations to see that you do arrive at the same weights and biases or not. Keep in mind, that's not the solution. There are different sets of weights and biases that can also work. So that's not the only solution. Okay? All right, so let's go on what we are going to talk about today. So what is a language model? Who can give an answer? If any of you have done a course in formal language, automata theory, or anything related to that, you have some idea of what a language is, right? The only thing that we're going to do today, or what we're going to do here, is that how do you model a language? So we are also going to differentiate a little bit. There's no slide, but I'm just going to talk about it. Is that what's the difference between like what you have done in automata theory or formal study of formal languages and creating a model for a language? So, who remembers languages in automata theory? Has anyone done that course?
Set of symbols, alphabets, and combining that we can form words, and we can make a set of those also that can be called a language in automata theory.
Right. So you missed one key concept, grammar.
Grammar, yeah.
Right. The grammar basically tells you how do you make sentences out of the words, right? Okay. So in that sense, you were starting with a grammar and the set of words and then trying to construct the sentences. If you think about it, ChatGPT is doing more or less same, because it's constructing sentences in response to whatever prompt you are providing it. Is it using the grammar and automata theory? Yes, no, maybe? Yeah? Yes, no? Okay. I think the right answer that I can provide is that we don't know. It has not been taught or instructed about those grammar rules explicitly. Maybe it has learned, because what we had provided the model is a lot of data for unsupervised learning. Maybe it has learned those rules, but nobody actually explicitly provided those grammatical rules to the model. That's for sure, right? We haven't done that. Why did we need that model? Does anyone remember that? As a computer scientist, why did we need a language model or a grammar or a language definition or context-free grammar or whatever we have learned about it as computer scientists? The primary use case there was that we should be able to write a program which can figure out whether a program or a statement or a set of statements is a valid program or valid text or valid sentence for that given grammar, right? And what else we were doing? You take a Python language program, translate into a machine language. So what you were doing, you were basically saying that let me parse the Python language, let me run it through the grammar to see if it's a syntactically valid program, and then somehow translate into a machine language that a computer can understand. That's what we were using the grammar for, right? More or less the same thing will be done here, except one big difference. We expect this model to actually write the program itself. So two basic differences. A, we are not telling it what the grammar is. All we are doing is that we are showing it like hundreds of programs written in Python, thousands of programs written in Python. Hope or expectation is that it will automatically figure out what the grammar is. And then not only it can check whether it is a valid Python program, we expect it to generate the Python program, right? Did the people who were developing the language model, did they expect it to happen? No. Actually, to begin with, they were pleasantly surprised that the model can actually write the program. The first thought was that maybe somebody is asking it to write a program to generate a prime number. Maybe it has seen a program because we have already fed it all the programs as a data, learning data. Maybe it has seen already that somebody wrote a program to generate a prime number. Maybe just it's remembering, it's just recalling. It's storing all the data as a fact database. That was researched a lot. I mean, even now, one thing is clear, that it is not necessarily reproducing those programs. It is writing the program. We still don't know what exactly is going on for it to figure out how to write a syntactically valid, a lot of time even semantically desirable program of what it is doing, right? Okay, so that's the language model. Slightly expanded use case compared to what you do typically in the language design or translator design or compiler construction, right? Okay, so given that background, what would be a language model roughly? Add that whatever we learned in the last couple of days, 3 days, about what the ChatGPT or any of those kind of generative AI systems normally do. What would a language model be? So one of the thing I mentioned here, and you guys need to actually come up, right? Because I will just, we said that what the generative AI is doing is that it's a probabilistic generation of the next possible word in a sequence of words. That's what we are doing here. So if you think about it, if let's say you have set of tokens which are allowed in a vocabulary, so x1 to xl belongs to vocabulary V, then the model assigns probability to each of these tokens so that it can figure out what's the next most probable word in a sequence of words that it has already seen or generated or provided with. Does that make sense? So basically what we are saying for us, because our problem domain is generative AI, where we want to generate the text, a model for us, a language model for us is a set of set of tokens, right? Or the set of tokens are assigned a certain probability. That probability tells the model which is the next best word in the sequence that it's working on. Clear? That's all about the generative AI. Now, in between, I did not use a specific word, but if you think about it, it's not just a simple probability. The probability that it is using is Bayesian probability. Now, someone remember from yesterday what was Bayesian probability? The Bayesian probability describes if you have two or more events which are interdependent. I didn't use the term interdependent yesterday because when you are calculating joint probability of two events, you have to determine whether the events are dependent on each other or independent of each other. When they are independent of each other, the probability calculation is very simple. You just add the two numbers. Right? Did we take an example yesterday or day before of finding out probability of a joint events which are mutually independent? Yes, no, maybe? Rolling a dice. When you roll a dice, first time you rolled a dice, you got 3. When you're rolling a dice second time, is the output of the second roll of a dice dependent on the first one or independent? Independent. Right. So you can add the two probabilities to find out the joint probability. Whereas the example we saw that where there was a jar with blue and red balls, is drawing the second ball dependent on the first ball or independent? Right. Why is it dependent? Correct. Because you have changed the number of balls in the system. If the first one was blue, the blue has gone down. If the first one was red, the red has gone down. Okay? To find out the probability of the joint events when the events are dependent on each other, we use Bayesian probability rules. Okay? So, what is happening here? What do you think? Why should we be using Bayesian probability rather than the simple joint probability in this case? Come on, think about it. The next word.
Next word is dependent on the past word.
Correct. So basically we are not randomly picking up a word. We are trying to make a meaningful sentence. So to get the meaningful sentence, the next word should be dependent on what is the word up until now, or what is the sentence up until now. So really speaking, what we are saying that, let's say a very simple language model, our vocabulary only has 5 words: 8, ball, cheese, mouse, and the. Right? So if we want to construct a model with this vocabulary, what do we need to do? We need to calculate Bayesian probabilities for each of these words given what we know up until now. So maybe the model, and I'm not saying how we are assigning it, assume that the model comes up with this, that probability of having a sentence like the mouse ate the cheese is really low. The cheese ate the mouse, even lower. Mouse the cheese ate is literally 0. right? Now, how do we know that? Because we attached some meaning to cheese or mouse or ate, right? You show it to a 2-year-old, maybe, and let's say 1.5-year-old, for them they are all same, right? When the baby starts learning, they're not constructing the sentences according to grammar. They just blabber the words, right? Is anyone teaching them grammar? No, they're just observing. And then they realize that I can't say cheese eat. I want to say I want to eat cheese. So they learn this. That's the same way this model is going to learn. Now, so these probability have been assigned that the combination of the words coming in a sentence in that order are higher, lower, or null based on whatever learning it has done, right? So very simply, what we are going to do is that for any model, we need to find out what the vocabulary is, and the learning will assign these probabilities. Now, keep in mind, yesterday or up until yesterday, I said that in the case of neural network, it's the weights and the biases which that's part of the learning. When you are going to use your neural network to create a language model, understand that there's going to be a softmax layer at the end somewhere. That layer would basically have all the words in the vocabulary there, or all the most probable words of the vocabulary there, and associated probability, so it will pick up what's the next possible word, right? Can you control, even after these probabilities have been calculated, can you control which word the model should pick? Yes, no, maybe?
Yes.
How? Come on. That's what we said, the parameter tuning. We'll come back to that again. Top P, top K, temperature. That's what all we were trying to instruct the model, that even though you figured out the probability, but we want you to still have some randomness, some control, or based on what we need, some changes. All right, so that's what the language model does. This was a very simple one with only 5 words. English language has 40,000 words, 60,000 words, depending on whatever the case may be. We'll also see as we go along, it is not necessarily the word that these generative AI systems are keeping track of. They are using something different than the word. That's also something that we have discovered. Okay. Just like we've done in the last 3 days, is that we continue to discover some new terminology or some new term. The language model that we are going to also use is called something called an autoregressive language model. Has anyone come across the term autoregressive before? No? Anybody who's done time series analysis or time series data or a data over a period of time? Statistics, a little beyond the high school or intermediate level statistics? No? Right. Okay. So autoregressive language model basically is trying to use what you have seen, that's what it is called, and then use that to predict the next word. Once you have predicted the next word, you actually use all of that to predict the next word. Okay? The learning that is happening here is by, and actually I'll come to that a little bit later as well, is by comparing with what it is predicting and what was provided to it. And that's why it's called autoregressive. Okay? I'll give you the example of that. So, going back to the chain rule or the Bayesian rule of probability, probability of having those 5 words in that order depends on probability of first discovering the, or first word of outputting as the, multiplied by the probability of having mouse as the next prediction given the was the first word, then the probability of having 8 as the next word provided the and mouse were the 2 first words predicted, and so on and so forth. That's the probability of joint events when they are not mutually independent. That's exactly what we are doing. So really speaking, what you're doing is that it's a conditional probability distribution of next token xi given whatever the tokens from 1 to I minus n. That's what the language model is doing. Is that clear? That's exactly what is going on in every generative AI model, be it Llama, be it Gemini, be it OpenAI, any of these things. They're all like this. All you're doing is calculating the probabilities and then picking up the most probable, least probable, random, top K, whatever the case you are provided by the whoever has tuned the parameter for the model for a specific task. Is that clear? So what happens here? I've introduced already 1 by t, because if you remember that, T0 was the, what was it? Higher the temperature, more random, or lower the temperature, more random? Right. It really goes back to thermodynamics. Higher the temperature, more movement of electrons around. So higher the temperature, more randomness, lower the temperature. So what's happening is that you're multiplying it by 1 by t, which means lower the temperature, less randomness, higher the temperature, more randomness, right? T is the temperature that controls. T equal to 1, sample normally from the pure language model. You go less than 1 or more than 1, you're changing it accordingly. Does that make sense? Do you guys think that if that is what a simple language model is, this is what you could use for doing all the work that the OpenAI is doing for you? Does that make sense? Okay, one of the examples you see that there was an article published in 2007. Has anyone seen this before? If not, just read it and let me know what you think of it. And the fact that it got published on January 3rd is purely incidental. 17 years ago, 18 years ago. Anyone here who has interest in astronomy, astrology, or any of those kind of things? Black hole theory? Nothing. All right, so what do you think of this? Looks like realistic, right? It's totally made up, generated by a generative AI. So even 18 years ago, we had systems which were generating fairly decent articles which look like real, not real. Okay? This is just an example here. Let me introduce another word, another term. The term is new, but we have all seen is that in-context learning. What is an in-context learning? Same as prompt engineering. We are trying to provide a context, and while providing that context, we are providing some supervised clues to the model so that it can answer the question. So if you think about it, if there was an answer given by a model like where is Stanford University, and it says Stanford University in California, it's a correct answer, but not sufficient to say if that was your intent. If you were trying to find which city it is in, it is not giving that answer. If that's what your intent was, how would you tell model that, or how would you provide it in context learning? Any idea based on what we learned in terms of prompt engineering yesterday? Was it yesterday or day before? Day before, I think. So you're going to give it an example saying that Washington University is in Washington, D.C. So it will say, oh, you're looking for city as well. Then it will say Stanford University is in Stanford, California, whatever the case may be. The point I'm trying to make is that the language models can do in-context learning as well. Now, why can they do it? Because probabilities are not pre-computed. The probabilities are conditional probability. If you provide an extra condition, the model can regenerate all the probabilities. Make sense? Yeah? Okay. In context learning, there's a slight difference with the supervised learning. I used the term supervised learning until yesterday, saying that you start with unsupervised learning and then you provide the supervised learning. What the slight difference between the supervised learning and the in-context learning is that, generally speaking, you expect, and which is what usually happens, that the model forgets in-context learning. So it need not be. It's basically in the context of your current prompt, it learned something. It may or may not retain it. That's the difference between in-context learning and a typical supervised learning that we are providing. Does that make sense? Now, the emergent behavior, that's also one term that I used 2 days ago. When the researchers realize this in-context learning that it is happening, that if we tell it something more while giving the prompt, that was an example of emergent behavior. I have a few more slides that we will talk about some other emergent behaviors that were observed. But if I ask you to define the emergent behavior, it is something that model performing that it has not been explicitly told how to do it. It learned on its own, right? A very simple example I gave you, that model was asked to provide the CAPTCHA, and it basically outsourced that task to a human to say that, can you do it for me, right? That's what is like an example of emergent behavior. Make sense? Okay, now think about it, the language model that we are going to have, or which the ChatGPT has, it doesn't have the 5 words, right? It has a lot more words. What's the best way you can think of storing all the vocabulary of a language? Any idea? So yesterday we talked about that we had a system whereby we were trying to recognize the handwritten numbers, digits. If you remember that, we were storing each digit as a 28 by 28 array, or a matrix, or a grid, whatever you want to call it. You got to find some representation for our words as well, right? So typically what happens is that we represent cat as like CAT and attach it to a natural phenomena or an object or an animated object or an animal called cat, right? I mentioned it yesterday. The language model doesn't know what cat signifies, or that's what we think, right? Which is what the emergent behavior and being sentient means, because, and we'll see a couple of slides later on. I'm not sure, okay, I have a slide or not, but we'll talk about it. Researchers started seeing behavior that seems to suggest that not only the model knows that CAT, cat, is a word, but also has some kind of understanding that cat is an animal. It's a feline animal, and what kind of shape it might have. May have a tail, may have 2 eyes, may have furry skin. All of that is emergent behavior, or the so-called sentience. So not only the model which we think about, for that model, the cat, CAT, should be just another symbol. We human are the only ones who know that the cat is a specific type of a pet or an animal. When researchers start discovering that the ChatGPT not only has cat as a symbol, but also has some understanding of what the cat looks like, that's when they start saying that, okay, something that we never told it, but starts realizing what a cat looks like. All right? And there was an experiment. I'll talk about the experiment. I think I don't have a slide here, but we'll talk about it when we. internally, each word like cat or dog, or for that matter any other word, is stored like a vector of numbers. We talked about it yesterday, right? Everything is a vector. So how big is the vector? It depends on the size of the model. We'll talk about it, how big the size of the vector is, which is used to represent each one. But for now, just think of it this way. Any word, every word, or a sequence of word is represented as a vector, which is a long list of numbers. When I say long list, it's as long as maybe 100 numbers, maybe 200 numbers, maybe a couple of thousand numbers, depending on size of your model. Okay? That's what each word is. Such a vector is called word vector. Okay? Now, if you think about word vector, an analogy, how many of you are familiar with latitude and longitude? What are those? Coordinates in, you have to be more specific. These are coordinates in a spherical coordinate system, and any point on an earth can be represented. Sorry? Okay. Let's not complicate it. Mapping is something totally different. Okay? Those who are doing the remote sensing and geographic information systems should know the difference, but that's fine. Basically, all I'm saying here is that these are spherical coordinates. What's the difference between Cartesian coordinate and spherical coordinate, if anyone knows? I mean, it's irrelevant, but I'm just saying that. And which one is the third? There's still 2 dimensions. There are only 2, lat long, right? These are angles. That's the difference, right? Okay, all right. So the point I'm trying to make here is that the analogy here, the cat is represented by a vector. The latitude, longitude is another vector. So if you say New York or London or Paris, they all have in a coordinate system, in this case, the spherical coordinate system that we can use to attach to any point on the Earth's surface. We have the system. So there might be a model somewhere which associates latitude, longitude to a word which happens to be name of a city, and then you can say that I'm using that vector to represent the word Washington DC or New York or London or Paris, right? What does it do for you? If you think about it, the benefit here is that just by looking at the names, you can't tell whether Washington DC is closer to New York or Washington DC is closer to London. But your word vector or the choice of the vector can tell you the proximity there. Why? Because if it is representing the globe, you can say it's spatially locating these cities in a given coordinate system. That's what it says. New York is closer to Washington DC because 38.9 is close to 40.7, not to 51.5. Makes it easier, right? So what we did here, if you think about it, we took a one-dimensional list, Washington DC, New York, London, Paris, which does not tell us the distance between each of them or proximity of each other. We converted into a higher dimension representation, 2-dimension here, which let us discover the proximity. Yeah? That's what these models are doing. I mentioned to you yesterday in the sense that it takes the words or it takes the data in lower dimension, explode it into a higher dimension so then it can use a linear function to separate them. The fact that you could separate it out saying that London is not close to Washington DC compared to New York is, which means that you can draw a line which put Washington DC and New York on one side and London on the other side. You can't do that just by looking at the names in one dimension, but when you put it in 2 dimensions using the latitude and longitude, you could do that. The same intuition applies when we say that you take any language model, what it is doing is that it is trying to convert whatever concept, word, or sequence of words into a much higher dimension knowledge. The benefit you get is that in higher dimension, it can find a linear separation or a function or a linear function that can help it distinguish proximity, closeness, similarity, whatever the case may be. That's what it is doing. So if you think about it, the cat is displayed, let's say here, in 90 different dimensions. So theoretically, let's say if you're trying to differentiate between dog and cat, somehow the model is learning 90 different ways to separate the two. It's not just 90, because theoretically it's not linear. See, as a human being, it's very difficult for us to visualize more than 3 dimensions. 4th dimension and you have a problem. Does anyone know what's the most common way of showing 4th dimension? Time. X, Y, Z and time, right? X, Y location, then you use the Z location as in terms of the height or depth. The 4th dimension that we can comprehend is time, right? Imagine thinking about like in 100 dimensions, 90 dimensions, 1000 dimensions. It's just incomprehensible. That's what the machine is able to do, and then figure out how exactly we're going to move and think about it. All right, make sense here? So same thing is explained here. What we are learning about how model is learning, that somehow it has figured out dog, kitten, pet, cat are related to each other. In some higher level dimension representation, these words appear closer. So the model knows that they're very somehow related to each other. Make sense? Okay, let me ask a slightly related but not exactly the same question. Has anyone heard of this term called dimensionality reduction? The reason I'm asking is that this is something what we all used to learn, we still learn. I learned this first, then this. Here the approach was that because we cannot deal with higher dimensions, we were always trying to reduce the dimensionality of our data. Anyone has heard this? No? How about this? Principal component analysis? No? Okay, I'm just giving the examples of some of the things where you may have come across these same or similar concept. Now, I haven't spoken to you one-on-one at what your topics of research are, those who are doing research, but these should be of interest to you. Doesn't matter what area you work on. One more thing, let me just ask this, which is a very similar concept. Eigenvalue, has anyone heard the word eigenvalues? Yes? No? What is eigenvalues? It's a linear algebra thing that you may have come across somewhere. Sorry? You have to go a little further than that. Hi. So what we were trying to do is that eigenvalue of a matrix. So a matrix, basically, if you take a large matrix here, the eigenvalues capture a smallest representation of whatever is contained in that matrix. Do you think have you ever used them? I mean, other than in the assignment that you calculate the eigenvalues of a matrix somewhere. You think you've used them somewhere? How many of you watch YouTube or streaming video, let's say? Come on. Everyone, right? if we did not know how to calculate eigenvalues, you would never see the YouTube. The streaming video is not possible without doing this. So what happens actually, there are metrics terminology or metrics calculations which reduces the size of a matrix while keeping the information content as same. So any compression, especially the video compression, is doing lot of metrics eigenvalue calculation and then sending it across and then recreating it at the receiver end. Okay. The reason I gave all of these examples was that in general, prior to the language model, the effort was always on dimensionality reduction. While I'm defining that, let me also explain what principal component analysis is. If you are having, let's say, 5 different attributes of something that you're observing or 10 different attributes, principal component analysis says that can we find a smaller set of attributes which allows us to capture everything about what we are trying to observe. That's principal component analysis. So trying to figure out which are the principal components describing the change. This is going in the other direction. Here, as a human, we are trying to reduce the dimensionality because we cannot comprehend the larger system. Here, the machine is trying to increase the dimensionality because it can do a lot more in the higher dimensions than we can do it. Okay? Clear? Hundreds of dimensions, thousands of dimensions. Actually, the current standard is thousands of dimensions. GPT-4 has, I think, 8,000 dimensions or 8K dimensions that it can potentially use to have the learning. Huge difference and huge gain in analysis. Human mind can't even kind of think about it. Does anyone know what kind of learning the machines are doing here, or what kind of learning these models have done? And it's a kind of a loaded question because, as I said, that researchers are still trying to figure out how and what is happening, both how and what. In terms of what, they have observed a lot. So let me give you some examples here. What they have figured out that the distance between men and women is exactly same as that of a king and queen. So the model is learning what women is to men, queen is to king. Now that's the emergent behavior or sentientness. Initial understanding was that it shouldn't know what king is, what queen is, what men is, what women is. But researcher discovered that not only has it understood what they mean, but also that the relative distance between men and women in some dimension is exactly what between king and queen. Not exactly, but pretty close. So if you think about it, king, I mean, what do we know about king? King is just a label. We associated king to a king-like figure and authority, or someone who leads or owns or rules on something. That's what is a concept that we as a human have defined. It may not yet understood that, but we don't know that for sure. But it has understood what queen is to king is exactly same what women is to men. It has also understood that what biggest is to big is same as smallest is to small. So it's also learning the degree. That relationship, no one has told it exactly, but it has figured out. Right? Now that's what is learning. So in a way, what they did is that they took the vector for biggest, subtracted big, and added small, and they got smallest. So in some dimensions, it has figured out the relationship between all these words on its own. Is that good? Is that bad? When the researchers, so some people are scary because it's learning things which were not told, and we don't know what else it has learned. But some people think that this is great. It's really learning and it will be helpful. So we don't know. The result is always there. It also has figured out what Swiss is to Switzerland, Cambodian is to Cambodia. So all of this learning is happening in higher dimension. What Paris is to France, Berlin is to Germany. Nobody told us explicitly the capitals. It has figured out the capitals. What unethical is to ethical, the possibly is to impossibly. It has learned the opposites. It's also learned the plurals. It has learned the gender roles. So there were a lot of learning that has been observed, and that's where gives the people a thinking where they think that something of interesting is happening in higher dimensions. Does that make sense? All right, let's just continue on it. One of the problem that we have with this, actually, it's learning from the language that has been fed to it, unsupervised learning. So, if you think about it, it is learning all the biases that we have. How did they find out? They took the doctor minus the men plus the women, and it says that's nurse. So the model has learned the gender roles, saying that if there is a doctor, it is going to be a man. If there is a woman in that medical role, it has to be a nurse. Why is that happening? Because that's our language. So this is something we'll talk the next week, in the sense that the biases that it is learning. So whatever is present in our human language, it's also learning that without realizing. Nobody's trying to say that that's what it is, but it's learning that as well. Okay? So these are some of the issues that we need to figure out. How do you figure out? Because this is a bias, and it will know it without anyone realizing it, and it can use it in right way, wrong way, or totally unexpected way. We don't know. Right? Okay. It's also trying to figure out sometime the numbers. If you ask a computer to compute 2 plus 3, it knows it, but the natural language may or may not give you the right answer. So a simple mathematics, it may not do it. Right? It may do it, it may not do it. It can do a lot of things, but not everything. It can figure out the mistakes. His, her, customer asked the mechanics to fix his car. Invariably, it says the car ownership is associated with a man. Right? Now that's just its learning, because that's how our language is. Anytime it has seen a sentence with car, it has seen a masculine pronoun. It has no idea of masculinity and the pronouns which are masculine or feminine, but it's learning that. Professor urged the student to do her homework. Okay, all right. Problem here. It may not realize what her is referring to. I'll have a few other examples here. Fruit flies like a banana. What is flies? Is it a verb or is it a noun? Why? It can be a noun also, fruit fly. Right? So what I'm saying is that it's learning a lot of things which are intended, unintended. Some of the things are right, some of the things are not right. Okay? All right. So word models, there are 3 different architectures that are being used right now. I'm going to take a very high level look at them right now. We're going to come back on those a little later. Decoders, encoders, and encoder-decoders. The difference between these 3 at a very high level, which is what the focus of today's talk is. We'll go into the detail tomorrow, and then the next week, the early day one on the next week. Depending on what you are trying to do, you can be following one of these 3 models. Let's just look at it a little bit more on a very high level. The decoder-only models are called autoregressive, left-to-right LLMs, or causal LLMs. What they do, they predict their word left to right. That's something that we talked about up until now. Bayesian probability, you start building the sentence from left to right, keep figuring the next word, next word, next word. Okay, so that's a decoder-only model. They are used for certain purposes, and they work very well for some kind of examples. The encoders, these are masked language models. So what they do is, what they're doing differently is that they're not directly going left to right. What they will do is that at some point of time, they will go back, they'll mask a word that they have already discovered, and then say, can I find a better word? So they are trying to predict by looking at the words on both sides. So if you think about it, if you're only looking at what you have already discovered, you get certain amount of intelligence or certain amount of skills. If you start predicting words by looking on both sides or improving the words, they are really a lot better here. Usually fine-tuned on supervised data for classification tasks. I mean, usually, not always, right? Then you have something called the encoder-decoder model. What they're trying to do is to learn or train themselves to map from one sequence to the other sequence, like translation, speech recognition, machine translation. So they're trying to look for, can we copy from one to the other one? Right? Now, if we focus ourselves on the language model, right? If anyone remembers that, what kind of applications can it have? Can the language model be used as sentiment analysis tool? So really what we are trying to do here is that, which is again somebody, if you're doing a research, you're always looking for, how can I reuse this? How can I use it for something else? So yes, really speaking, what you're saying is that you're trying to frame it in a way that, given this sentence, what would be the next word? So you say that, what's the probability that the next word is positive given this is already known? The sentiment of the sentence is, if the language model looks at this, is it going to say positive or is it going to say negative? So you can use the sentiment analysis sentiment analysis task by converting it into discovering the next word in the sequence. Yeah? Can you use the summarization task? You can feed the summarization saying that this is given to you, and you're saying that, given this as a prompt, summarize it or write it in one sentence or redo it in one sentence. Okay? The bottom line, what I'm trying to point out here is that there are multiple ways you can utilize the same information or same set of information or same language model, but can have it do multiple things. I'm going to take one large deep dive into how exactly it is working, but again, it's a very high level, deep dive but very high level. We'll go into this detail most likely tomorrow. So what's going on here is that you are feeding this information in, let it go through multiple layers and something called head, which is attention head. We haven't yet talked about what attention is. We're going to talk about possibly tomorrow. If we can, and then have it generate the summary. So the original point I'm trying to make here is that if we have a good language model, we can actually use this to do a lot of different kind of tasks. So think about it. We started, the intuition of the language model was that it will be predicting the next word in a sequence of words. Then we looked at it, that's saying that, okay, there are three different type of models there, coder, encoder, and both coder and encoder. And what they can do a lot more. Not only they can predict the next word, but we can morph another problem, sentiment analysis, summarization, for example, and turn it into a problem that is, for a language model, exactly as predicting the next word using one of the underlying architectures. Make sense? Okay, so something that we talked about earlier, in context learning or supervised learning on top of what the model or a base or foundation model already knows, or prompt engineering. Let's look at in the slightly different way now, because now we know slightly better in the sense that what our language model looks like. Each word is represented by a list of numbers in a higher dimension, and then every combination of these words has an associated probability. So let's see, how do we translate the in-context learning or prompt engineering in terms of probabilities that we have associated with each of these words or terms, right? So two main things actually, because you're choosing a word based on the model's probability, that's called decoding. And then which one of the word you pick up is sampling. We have used the word sampling before. You have a distribution, and based on that you're picking up a specific word. That's exactly what's going on. A sampling is randomly picking up word, and then you're controlling that which word to be picked up, And that's exactly what you would do, and figure out that what is the next word that you can control by tuning the parameters. I think the next few slides will go over the same things and try to map that or help you understand that which of these parameters will make a difference based on the probability here. Now, a little bit of math. Okay, let me ask this one question here, is that, were you guys comfortable with the amount of math we covered yesterday, or was it too much or too little? Can we go more or less? Sorry? Too much? Okay, all right. More than 3/4 of you didn't even respond. Only few are saying something. Yes, no, what? Yes. Okay. All right. So let me just bring it a few more concepts here. So we talked about the probability distribution, right? How many of you have used or heard the word called tail? Long tail or short tail distributions? Any idea what those are? How do you define a distribution? Okay, so a probability distribution function, PDF, basically looks like your example, right? What was this? Okay. How about this? I don't think it's skewed. Is it normal or not? It's not? Why is it not normal? Sorry? All right. How about this? Not normal? Why? They're all normal distributions. Right? I have not introduced the skew yet. Somebody said skewed, right? What is a skewed distribution? So a skewed normal distribution will look something like this. Still a normal distribution. If they are all normal distributions, how do you differentiate between them? Come on, guys. No. Don't bring a new term there, but unless you want. How do you define probability distributions? Come on. Like one way is that you actually find a function, a polynomial that basically is represented here, but that would be a somewhat different one. Has anyone heard the term called moments? Yes, no, maybe? Mean? Sorry, what did you say? Okay, don't go back to your 10th grade mathematics because that's all you learned. Mean, median, mode is something totally different. I only wrote mean here. That's called first moment of a normal distribution. What's the second moment of the normal distribution? Yes? Correct. What's standard deviation? There are higher level moments also. Does anyone know what those are? No. And one more, if anyone remember. That's not the point. Point I'm trying to make here is that These are all normal distribution. Okay? What is mean? What value? The most common value. Right? That's your mean. What's standard deviation? The standard deviation says that around the mean, how it's distributed as standard deviation. Okay? What's skew? Right. If across or around the mean, the curve is exactly same, it has a skew of 0. If it is not, then it's skewed towards the left or towards the right, which means that in general the expectation is that the 50% of the values will be on one side, 50% on the other side of the mean. Not always true, it could be skewed. This is skewed to the left. You could have had a graph which would go like this, skewed to the right of the mean, right? What is tail? Majority of the values would be close or very close to the mean. Normally in a normal distribution you say that what? 2/3 of the values will be within 60% around the means or something like that, right? Whatever is outside these two standard deviation is tail on the left side and on the right side. Depending on the skew and standard deviation, you may have a tail which is a very short tail or a long tail, a fat tail or a thin tail. What does that mean? Any idea? Come on, go ahead. So one thing I'll say, guys, like the math is very fundamental actually, and these are basic maths that you should remember and be able to recall very quickly. So the probability distribution is actually modeling some phenomena. That's what it is happening. You are sampling from a naturally observed phenomena and trying to represent it by a function. Understand one, function is nothing but mathematically representing a naturally occurring phenomena. Whether it's the chirping of the bird, whether it's the type of the flowers, the shape of the flowers, number of people in this class, your age, your height, everything can be represented as a function. Why do we need it? If we are trying to mathematically model anything related to anything outside there, it's all functions. So the distribution of the probability is the occurrence of a specific value in a distribution. Long tail means that there are a lot of observations that are possible, but we have very low probability. Right? So think of it this way. Let me ask you this. Very simple examples which you should be able to relate: the age and height. What do you think? Is it going to be a long tail distribution or a short tail distribution? One of the things one of you guys asked is that how do we test in my institute there, but I tell you one thing is that there's always think of it, that this is a key difference the way I studied here, right? So I know a little bit here as well. The key difference between the way we study here is that we just learn the definitions, not think of how to use it. There we always try to ask you a question and apply it in the sense. So I'm asking you a very simple question, right? I explained to you the distribution, I explained to you the tails. Now I'm asking you the question, the distribution of height given an age. Is it a long tail or a short tail phenomena?
Short tail, sir.
Why do you say so?
As both are roughly comparable to each other, like go hand in hand, age and height.
So your answer is right, but the explanation is not very convincing. Anybody else? He's right. But why? That was not very convincing. You've all seen it. You've all seen it. What is a long or tail phenomena in a distribution of height. Either a very tall person or a very short person. How many dwarfs have you seen in your life? Very few. How many people above, let's say, 6 feet 3 inches, 6 feet 4 inches? Very few. So what does it tell you? It tells you that there is not a long tail. It's a very short tail here, right? So think about it. Now, one of the common things that we do if we are interviewing a student for, let's say, research in data science. What is data science? You're trying to map your mathematical modeling skills to a naturally occurring phenomena. So if I ask you to draw me a distribution of height, you should be able to draw a very close to correct distribution. If you draw me a distribution for an age that looks like this one, you haven't understood. Right? The distribution for the height against the age will actually look like this. Majority of the people will be here. Probably like 90% of the people will be in a very close range. If you take the people, let's say height of people of the age group 18 to 21, you'll probably find, let's say men, because men, women, slight difference. Men should be in 5 foot 2 inches to 6 foot 2 inches. 90% of them will be there, short tail. So there are certain basic things that you've got to make sure that you understand. All right, same thing applies here. Okay, given a specific situation, because we are saying that it's all probability distribution, the moment I say distribution, all of these things come into play, right? And depending on whether it's using a skewed distribution, a long tail distribution, a fat tail distribution. I didn't define the fat tail. Can someone tell me what is a fat tail distribution? The fat tail distribution will be something like this. So the mean is there, but mean is not very prominent, and the tail is very fat. So a lot of words or a lot of possibilities exist there. Okay, let me ask this question just to test if you have understood. Give me an example of a long tail distribution phenomena. Go ahead. Yes, no, maybe, whatever. Sorry? That's a good example. Yes, if you draw an income distribution, you would see a long tail phenomena. Would it be a fat tail or thin tail? Okay, not fat. Skewed or not skewed? Right. How many of you agree? That's a great example. Not that I was thinking about, but that's a great example. I'll tell you what I had in my mind when I asked this question. Has everyone understood why the income distribution is going to be a skewed long tail phenomena? Is that point clear? That's a great example actually. Is that clear? So, if I ask you to draw the income distribution curve, what would it look like? Without even knowing the exact numbers, right? Let's say this is whatever, X. The number is going to, the graph is going to look like something like this. This would be your, what is it called? Mean income. Well, let's call it mean income. I was trying to think of some number, right? There might be something like a poverty line. Some people are below this, some people are in here. and there's a very thin tail which shows people who are earning 10 times the average income, 100 times the average income. You might have Tatas here, you might have Ambani here, and things like that. So you have, and it's skewed because on the right side of the mean, there are fewer and fewer people, but there are a lot of people who are earning a lot more than the average income. Okay? So that's a great example of a skewed long tail on one side, fat tail on the left side, because a lot of people are here who are earning less than the number, whatever that is, right? So if you go by what I told yesterday, that functions rule the world, you should be able to have a good understanding of any naturally occurring phenomena and be able to draw the line. One of the one of the interviews that I gave, and this was year 1987, was just this actually, very similar to, how many of you have heard this place called Tata Institute of Fundamental Research? I didn't join it, but most of the questions were just this: draw the function or draw the curve. Or the other side was that given a curve, can you write down the equation of that curve? Not exactly, but like similar thing. So it hasn't changed. 40 years ago, the functions were important and the curves were important. Today also they are important. Okay, all right, so where were we? All right, so what the language model is doing, if the language model is picking up based on a probability distribution, obviously it is important that what kind of distribution is it learning or figuring out. Because if it is figuring out the wrong distribution, then you have a problem. What problem can it be? I have given an example. And by the way, I wanted to give the example that I had for the long tail distribution. I'll tell you that also, what I had in mind. But what problem do you think the language model can have if it is not finding out the right distribution for the underlying words? I gave one instance of that happening in the last couple of days. So, I gave you an example of Microsoft, I think it was Microsoft, coming up with a model, chatbot, and it very quickly learned the cuss words and was always producing all the response with the cuss words. So if you think about it, in a normal language or normal conversation, the cuss words should be somewhere in a long tail of a very narrow possibility. They do exist, right? But how common are they, or should they be here? But somehow people using prompt engineering and the tuning were able to make a model which make a distribution which the model thought that these cuss words are not here but somewhere here. So it was sampling them a lot more than they should have been sampled. So what's the thing here? Because it's a probabilistic model, because it's sampling based on a probability distribution, it's important that you train the model to use the right probability distribution for your domain, for your task. If you don't do that, you'll get the wrong results or unexpected results. Make sense? Okay, all right. So, couple of things here is that the random sampling doesn't work very well because of this that I just explained. If the model discovers the distribution wrong, it has learned them, it has represented them, it has figured out the relative distance and everything, but if the sampling is wrong because the distribution is wrong, you get the wrong answer. Okay? Now, what I'm telling you here, not many of you, maybe none of you, I haven't trained the model myself, right? If I was working for Meta or for Facebook or someone or Google, maybe I would have had a chance. You would not be training the model. You would be actually either prompt engineering it or tuning it or kind of adding on top of the foundation model. So these are the things that you need to think about, right? You're not generating the underlying neural network. Maybe you will end up training something, supervised training at the top of it, But keep in mind what can go wrong. Okay? So, what happens here is that if you get the distribution wrong, you might get the weird sentences. That weird sentences may be the cuss words, the weird sentences may be the sentence which makes no meaning or whatsoever, right? So what you're trying to do, you need to find a ways to emphasize high probability words, or you want to emphasize the middle probability word, different ways to make sure that it is sampling from the right part of the distribution. Okay? All right. Now, let's go back and look at the tuning that we looked in prompt engineering. Top case sampling. It's rewritten here. I would actually ask you to read it and make sure that you understand. It's rewritten here in terms of the terminology that we started using today, which is vocabulary, context, the probabilities, and things like that. So, see if you can understand. If you don't, raise your hand and I'll explain it. Has everyone understood it or have a question or not understood it? Sorry? What's the issue with the fourth one? I was expecting it. There's only one word that I have not spoken, which is the renormalize or normalize. Is that what your problem is or something else? Okay. What is normal distribution? It's the same thing. We've been talking about the normal distribution. What is a normal distribution? Or what is normalizing a distribution? Yes, but that's not really a mathematical way of describing what a normal distribution is. So, normalizing a distribution means that the mean is 0 and standard deviation is 1. So, renormalizing a distribution means that readjusting so that the mean again becomes 0. Why do we do this? Because it makes the mathematical calculations easier. Because the mean is 0, standard deviation is 1, you can actually visualize it much easier, compare it very easier. If you're trying to compare two distributions which have a different mean and different standard deviation, it's not easy to compare them. Visually you can compare them, but for a program or computer to do it is impossible. So what you do is that if you need to compare, or even if you need to sample, you normalize your distribution so that the mean is 0 and standard deviation is 1, and then you basically use it. So what is going on in number 4 is once you have picked up a word, the remaining words, the distribution for remaining words is renormalized. So think of the work that these models are doing each time they emit the next word. They are renormalizing also, as in the step number 4, before sampling the next word. All right, is that clear? Everyone? Let's top P sampling. Remember we had a top K and top P also. So again, just read it. If you don't understand, I'll explain because I've already explained it earlier. Let's just try to see you can associate it with today's terminology, the concept that we introduced yesterday. Oh, this is not complete. All right, sorry. So this is also something that you need to do, is to figure out that how exactly we kind of merge the concepts with the new terminology, roughly. Everybody is clear on this, or any questions? Just the mathematical way of saying what we talked about from the user perspective and what prompt engineering is. All right, so let's move on to the temperature sampling. Again, the same thing. We talked about it from the user perspective. Now we are saying is that what does it mean in terms of probabilities? Now, it's not saying this, but think about it this way. Going more on the tail or staying more in the middle around the mean. That's what is increasing or raising or lowering the temperature is. It's easy when you have a single output or a sigmoid kind of layer, but if you have a softmax which has a variety of distribution, that's where what you do in the sense that you let it learn through a temperature parameter and modify the probability based on the parameter that you have. I'll get you these slides. You can go, you can understand it. Everything that we have talked about, this is just a repeat of that in the language of probabilities and probability distribution. Other than that, it's very same. Yeah, no new term here. Everything that we have used before, whether it's distribution, temperature, tail, greedy, and softmax, everything we have defined more or less here. Okay, all right. Any questions so far? So what did we do? Let me summarize this so that hopefully you'll remember it, right? We looked at a language model. And what we said, the language model consists of word vectors. Every word is represented as a vector. Higher the dimensions of the vector, higher the dimensions we are trying to model. We said by going in a higher dimension model, the model learns a lot more things which are not explicitly told to it. We said this yesterday also, we said it again today also. Then we looked at the probability distribution. Okay, before we go there. Then we said that our language model is predicting one word at a time. That word is predicted based on the probability distribution using the Bayes probability, chain rule of Bayes probability. The next thing we said that even though it's predicting the next word, there are a lot of problems, be it sentiment analysis, summarization, content generation, that can be explained or that can be implemented using the next word prediction model. Then we said there are three different type of architectures. We didn't go into the detail. We just introduced them: encoder, decoder, and a combination of the two, and what kind of problems are they solving, and also what's the difference between them at a very high level, right? And then we said that prompt engineering, which was the in-context learning, how does that, what we talked about from the user perspective, translate to the probability and probability distribution and sampling? That's what we did, right? One other thing I kind of mentioned in the sense that because it's most likely majority of you would be tuning or doing the in-context learning if you happen to work with the large language models. Maybe very few, maybe none of you will actually be building the model of itself. If one of you do, great, nothing wrong with that. So you've got to understand what can go wrong and how do you fix it, or look for what the problems might be. So for example, if somebody asks you, of that instance when the Microsoft introduced a chatbot based on large language model, starts learning cuss words and then using those there, you can now understand and explain what exactly might be happening. I'm not saying definitive because no one knows for sure, but it was very obvious that it's sampling from either the wrong part of the distribution or had the distribution totally wrong. Now that was not intended. Somebody using prompt engineering forced the model to actually have one of the two things, either get the cuss words here because they actually gave the in-context learning of so much that the model said that maybe what I knew up until now is all wrong. Maybe all the language is like this, right? We don't know what exactly happened, but now you have a better understanding what must be going on inside there because it's all about probability distribution and sampling, nothing else. Okay? All right. Any questions? Okay, so before we take a break, we break at 11:30, so we have about 20 minutes or so. Let me introduce the next topic that we're going to cover. Nothing new here. We talked about the learning yesterday. Now we're going to look into an algorithm for the learning. Basically the same thing that we did yesterday, but use this with today's terminology, what we have been doing so far, in terms of the probability and the distribution. Make sense? All right. What were the different kinds of learnings? We've talked about it. Right. Supervised, unsupervised, and reinforcement, right? So, in a typical way, early machine learning algorithms were all supervised learning because general thinking was that if you give sufficient number of samples, the early things were basically differentiating between cats and dogs or recognition of the handwritten digits. So the idea was that if you show it a large number of samples, for example, which says that this is a 4, this is a 4, this is also a 4, this is a 4, then hopefully the model will learn and be able to say that this is also likely a 4, or incorrectly think that this is also a 4. Somebody they intended to write a 9 but did not connect it. Right. Supervised learning. You show enough samples of what the numbers and values are and they are basically learning it. The problem with that is, where do you have the data that's labeled like this? Sorry? So two things happened actually. One, obviously, they figured out the large language model where they did not need the explicitly labeled data. And second, what was the second one? Can anyone tell me where was the sampled or labeled data was being generated? Let me ask you a question differently. Have you worked for either Google or Facebook, helping them out for supervised learning? Yes, no, maybe? Yes? How? These companies got very smart actually. Every time you solve a CAPTCHA, you're providing them a supervised learning example. Right? How many of you use Facebook and have used the images and tagged your friends there? Every time you tag your friend, that's another supervised learning example. Right? There's already a case going on because they never told you that they are using your images and your tagging as a learning example, so they're already being sued in the US courts. Because, I mean, I'm sure they probably will find something because nobody reads those 50 pages of the agreement when you sign up the account. They may have a line somewhere there that this could become, but again, no one realized what they're doing. Like when they started doing automatic recognition of your friends in the picture, right? They were just doing this. they had trained their model based on your supervised learning by saying that this is my friend XYZ, this is my friend XYZ, and then they start improving their system for face recognition, saying that, okay, maybe this is also XYZ. Every time they asked the question and you confirmed yes or no, you were giving another reinforcement learning example. So first when you tag, you gave a supervised learning example. Then based on that, they started saying that, is this that same person? And when you were telling them yes or no, that was reinforcement learning. They were saying that if you said yes, they said, okay, these weights are right. If you said no, they said, no, the weights needs to be adjusted. So all of you have contributed in one way or the other to actually make these models what they are today. Right? And that's what like these companies do all the time. Okay, so this is where the supervised training algorithm came in. You just show it enough number of samples, and I think, yeah. Okay, now you move on to, because that is very difficult. The supervised learning is difficult because how do you generate the data? You need like a lot of people to generate the data, and even the reinforcement learning is difficult because you need people to every time keep saying that yes, no, right, wrong, right, wrong. They found a way around it, like all the users became unknowingly their data provider. But in general, the large language models use what is called the self-supervised training algorithm. Now, what would be a self-supervised training algorithm? Tell me. I mean, the algorithm is written there, but imagine that. See, this is what the research is all about. When the companies realize that they need supervised learning, they don't have data, what did they do? They made you as the people who are tagging and providing them example for supervised learning. Then they said that, can we do any different? In the case of language model, they figured out an algorithm to do slightly better. If you read through this very simple algorithm, can someone tell me what is going on here? So what is self-supervised learning is there. What the companies realize that when they are doing the large language model, they can use all the data that they have access to. Let's say they started with Wikipedia, right? It's generally available. In Wikipedia, they came across a sentence which says, we just train them to predict the next word. I'm just taking an example from here, right? What would the self-supervised learning do? It says that, let me try with we just train them and see what's the next word am I predicting. Am I predicting 2 or something else? If I'm not predicting 2 at some probability, then I need to tweak my model. If I have done all the way here, because I know that this is a supervised example, this is the correct sentence, can I predict this? Given we just train them to predict, am I getting the next word right or not? So what they did is that every text got converted into an example. That's what it's doing. Take the corpus of text, whatever the text is, let's use this one, we just train them to predict the next word. At each time step t, ask the model to predict the next word. Start with V and see if you can get just. If you got V just, can you get the train? You get the train. So use every sentence that you come across itself to predict itself. So you know what the right sentence is, can you predict it? That's what is a self-supervised training algorithm. You don't need someone to explicitly tell you whether this is right or not, because you are getting the right word. So in a way, what these models started doing that, can they generate the same Wikipedia entry that they are finding? Every time they come across a new Wikipedia page entry, they will test to see if they can generate it. That was the self-supervised learning. And if they were not generating the same next word, they were using gradient descent to minimize the error so that they can get to the same word. You do it over and over and over again and you start getting better. Make sense? Right? A minor difference to this one was the teacher forcing, which is the reinforcement learning, where in the sense that somebody is saying that this is right, this is wrong, this is right, this is wrong. So you start using it. You start figuring out that, okay, I'm not getting it right, let someone correct it, and then you do it. You can use the teacher forcing is the in-context learning also. You can use it in the sense that someone providing manual input of tagging or confirming whether they're getting it right or not. Make sense? So let's ask the question here. Whatever we have learned so far, what do you think was the most surprising thing for you, or most fundamental thing for you, or most powerful thing for you? In the sense that whether you knew it from the very beginning or you discovered something new, what do you think the key thing in your opinion that make these large language model as powerful as they are? Sorry? Self-learning algorithm. What else?
Connecting the relations which are not provided.
But that's the behavior observed, but how exactly? So we learned a few things like how they are representing, how they are using probability distributions, how they are using the matrix multiplication, the fact that they model as a synapse, as a neuron, and then they implemented it. Which one of the thing you think is the most important thing? So I'm trying to figure out, the question is that very simple learning things. I mean, none of the thing that we talked about was new. Matrix multiplication, probabilities, linear algebra, calculus, everything is all known to you. What is it that makes these things so powerful? Sorry?
Large pool of data sets.
Large pool of data sets. Anybody else?
Giving a direction so the world can be connected and predict the right knowledge.
Okay, back there. Sorry? More dimensions? Okay, well, which is more or less same as vectors because you have a larger vector size. So, I mean, this is an open thing. People are still trying to figure out, but a couple of things are very clear. That a lot of this emergent behavior started appearing only when you train it with larger data sets. That was very clear. Larger data sets also force it to go into higher dimensions. So that is also an obvious thing that we got to figure out. So if you think about it, if we have to think through it, is that the learning mechanism is very simple. How did it get into this powerful model? First thing is that the GPT-3 was trained on almost like 500 billion words. To put it in perspective, a typical human child by the age of 10, and we're saying typical, which is before these smartphones, when you are not reading books anymore, they were coming across 100 million words. So 500 billion, 500 billion word is many more times what a human child will see. So a lot of data that they have seen is the reason that these models become so powerful. And if you think about it, this fact, because the power is derived from the amount of data you have seen, is now making the researchers really concerned, because these models have now seen every single written document ever, which means that they have reached at the peak of their power. And that is happening. The current research has shown that if they start consuming the data which they themselves are producing, they are getting worse and worse and worse. So the synthetic data is a problem. We'll get to that next week when we start talking about the current state and the problems and then the issues and the situations like that. But the bottom line is here. Now, an unstated fact here in the sense that the fact that you can use 500 billion word to train, create these massive vectors and these spaces requires a lot of compute power also. So the fact that you can consume that much data and you have that much raw compute power is also a need. I'm just giving you a little bit of comparison between GPT-3 and 4. I've left out 1 and 2. 3 can only do text, 4 can do text and images both. 3 is comparatively less accurate, 4 is more accurate. About 300 apps were there for GPT-3, GPT-4 unknown because API is now published. You can create an app, which is what I mostly think that majority of you, if you want to work in the generative AI or the algorithm, that's where you will be doing, tweaking all the things that we talked about so far. GPT-3 had 175 billion parameters. Now, I think you should know enough about it, what these parameters are or were. Come on. What are these parameters? Come on, guys, I've told you like 10 times. Weights and biases. Right? GPT-4 has 1.76 trillion parameters. These are all learning is weights and bias, nothing else. The size of the GPT-3 model, which is the value. So if you say, what is the GPT-3 model? It's just a huge database of numbers, weights and biases. That's all it is. The GPT-3 could have been kept on my phone, 17 gigabyte. GPT-4 can still be here, 45 gigabytes only. That's it. That's all it is. The prompt length, the maximum size of 4K, this is 8K. So to a large extent, this also, not directly, but it can go up to 8K dimensions, which is what I mentioned, I think, earlier today, right? That's where, does not necessarily mean that it has to go that far. Majority of the time, GPT-4 is, you will see, like if you are having access to that level, it is constructing based on your prompt anywhere in 100 to 1000 dimensions, depending on how complex the prompt is. But it can go up to 8K. The speed, that's where the compute power comes. GPT-3 was generating 10 billion tokens per second. The token is not exactly same as Word, but pretty close. So if you started using it, sometime it will say that too many requests, like you can't generate or you can't ask it for another one. GPT-4 is 10 times faster, 100 billion tokens per second. So they've thrown a lot of compute power. So at some point of time, the question will come, at what cost, right? So you might be using it today for free of cost. Suddenly they'll start charging because it takes a lot of money to get that kind of performance, 100 billion tokens per second, right? So that's what it is. Now, if we just think about it, why does next token prediction work so well? Because that's all these large language models are doing, but they can do summarization, content generation, sentiment analysis, summarization, all kinds of things, right? Okay, where are we? We have 5 minutes. All right, fine. I'll stop at this slide and then we'll come back to it. Does anyone know what a theory of mind problem is? This is a very well-known set of problems in cognitive science. Do we have in the college institute here cognitive science courses? Does anyone teach cognitive science? No?
We have in humanities and social sciences where they are teaching psychology, industrial psychology or human resource.
Cognitive science actually is not neuroscience as in a health related thing, but more related to how the brain functions in a way. All right, that's fine. So the humanities department is not the right place to teach it, but somewhere, I mean, there could be. Anyway, so theory of mind problems basically says that can something think on its own? So, yeah, let's say. When you look at this, what comes to your mind? What's in here? Water. If let's say, instead of drink it up, it says something else. Wash your clothes well or something like that. Okay, just that. You look at it, you read it, would you think it has water inside it, right? Even though you may have seen this thousands of times and use it to drink also. That's theory of mind problem. So one of the way researchers were testing these large language models was, does the model or can the model solve a theory of mind problem? Which means if you show it this image and says that it reads use 1 spoon per wash cycle, and then ask the question, does it contain water? Can it answer yes or no? That's theory of mind problem in a way. So GPT-1 and GPT-2 could not solve this problem. They will always respond saying this, yes, it has water, because that's what they've seen all the time. GPT-3 was answering it 20% at the right time, depending on how you're constructing the prompt. GPT-4 is actually doing more than half the time it's getting it right, these kind of problems. So you show it a popcorn bag, and then say instead of popcorn, it writes chocolate, and then ask it, does it have popcorn? Half the time it's now telling no, because it says chocolate, it has chocolate. That's the theory of mind problem, in the sense that you're provided a prompt which is different from what you have been trained all along for. Can you apply your mind to say what the right answer is? So basically what you're saying is that truly understand the meanings of the words, which is where we say sentience, in the sense that chocolate is no longer a label. If its learning is that the red color paper bag is popcorn, but because the word says chocolate, there's a likelihood that it does not contain popcorn. So it attaching the meaning to the words in the training set. That is happening with GPT-4. So the question was that, is it really understanding the words, or they're just, because they've been repeatedly told red bag, paper bag contains popcorn, so it's just repeating it. Now that's the experiment that are going on with GPT-4. It's happening a lot. So what is going on, in the sense that it's learning the relationship between the words, and that's what both scary and interesting as well. Okay? All right, so why don't we stop here? When we come back, I said that I'll answer a couple of your questions as well. So what I'm going to do, I'll complete this. There are a few more things that we want to talk about here, and then move on to the other topics as well. Right? So when we come back, we'll continue this conversation, but we will start with what these large language models cannot do, or at least cannot yet do. So think about it, what it cannot do. Rather than, I mean, you can use it based on your own experience, what you try for it to do and it didn't do, or thinking in terms of what we learned, how exactly they do it, now you think that they cannot do it. Okay? All right, so why don't we take a break here, and then we meet in